Let's talk about sequences. So at this point of the course, we are mostly done with integration. It'll come up from time to time, but we're done with the complicated integration where we have many steps and we get these complicated answers and all this other stuff. I think mostly from here on out, we will mostly be doing pretty simple integrals, and it'll be pretty sparingly throughout the rest of the course. So the next chapter is on sequences and series. So you probably have seen sequences. I know they come up in algebra classes, and you may see them in pre-calculus classes. And so this will be the same thing. We're going to, of course, take this a little bit farther than you would have seen before. But the basics and the foundation that we're going to talk about today mostly should be fairly familiar, at least to some degree. So when we talk about a sequence, we're in this class only going to talk about infinite sequences. So there are infinite number of terms, but a sequence is just a list of numbers. And typically the numbers have some pattern to them. And not always, but most of the time we can get a formula for this. And a pretty straightforward formula. So we use subscripts to indicate the number of the terms. So a sub 1, a sub 2, so on. A sub n will just indicate the general term. And of course, there are infinitely many. So a sub n plus 1 is always going to come right after a sub n, and so on. So there are three equivalent descriptions of a sequence. One is to write just a general formula and put the curly braces around it. So that's one way. And then the other way that you probably have seen, I think that most of the time this is a typical way to write these in algebra classes. You name the sequence whatever letter you want besides n. So a sub n, b sub n, C sub n, and that equals whatever formula you're going to use. And so you could figure out the fifth term of the sequence by plugging in 5 for n, or whatever number you want. And then the other way is to list several of the terms. Of course, these are infinite sequences, so you're not going to list all the terms, but you could list enough to where you can see the pattern, and then maybe after ellipsis, you can put the general term just to kind of show what the formula is. So all three of those are typical ways to write a sequence. Okay, so here, this first example, we're going to write the first 4 terms of the sequence defined by this formula. And now notice n starts with 2 here. Most of the time n will start with 1, but it doesn't have to. It could start with any positive number. So just always pay attention to that. See where you're starting and then go from there. So we're going to start with n equals 2. So this would be 2 over 2 plus 1. The next term, n equals 3. So it'd be 3 over 3 plus 1. 4 over 4 plus 1, and so on. And then we can simplify these fractions, and we will get 2/3, comma, 3/4, comma, 4/5, and so on. Okay, so when we say, well, we write the first 4 terms, so I guess we're just going to write that, and then we, of course, dot, dot, dot after that. Now, write a formula for the sequence. So we have square root 3, square root 4, square root 5, so on. So we notice that each number under the square root is 1 more than the previous number. But we don't start with 1, so we're not going to write necessarily square root n, although we could. So we could write this as square root n, where n goes from 3 to infinity. So it doesn't really matter, since we're going up to infinity. We can start wherever we want and still end up with an infinite number of terms. The other way we could do this, if you prefer to start with 1, we could write the square root of n plus 2, and then start at n equals 1 and go up to infinity. So either way is fine, but just remember, you do not have to start with n equals 1 if it's easier not to. And sometimes it's easier not to. Just depends on the sequence that you have. All right, and then this one, write the first 5 terms of the sequence defined by this formula. Now, when you see this -1 to the n in front of, or at the beginning of your sequence formula, this is going to be what's called an alternating sequence. And what that means is terms are going to go from positive to negative to positive to negative, just alternating throughout the whole sequence. So once you get the first term, you can kind of ignore that -1 to the end because it's just going to switch signs every time, and that's all that one does. So let's see. So we'll just call the sequence A. So A sub 1 would be -1 to the first times 1 plus 1 over 3 to the 1. And so that gives us -2/3. So the first term is 2/3. A sub 2. Now, we don't really have to worry about this. We know the next term is going to be positive. I'll put it in, but we don't really need to consider it too much in the calculation. Then we have 2 plus 1 over 3 squared. So this would be 3 over 9, which is 1/3. Of course, this one is positive, so 1/3. Then the next one, we get -1 cubed times 3 plus 1 over 3 cubed. And so this will be negative. -1 cubed is -1, and then 4 over 81. Now, if you write this one, so when you simplify the fraction, sometimes it's harder to see the pattern. But if you, this should be negative, and then that one should be negative. But if you don't simplify the fractions, you can a lot of times see the pattern. So the pattern, the numerator seems to be going up. So you got 2/3, 3/9, 4 over 81. So this one's going to be +5 over something. And then the denominator is going 3, 9. Actually, this should be 27, not 81. 27. 3, 9, 27. So the next one will be 81. So 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. And then the fifth term is going to be negative, positive, negative, positive. This one will be negative. 2, 3, 4, 5, 6. And then 3 to the fifth, which will be 243. Okay, so, and you can write all these out if you want, but you don't necessarily have to write this part out. Kind of once you see the pattern, you can figure out the terms as you go along. All right, so next we have what's called the limit of the sequence. And this is really what we're more interested in for this class, the limit of the sequence. So what we mean by the limit of the sequence, and we know what a limit is from Calculus 1. So the limit of a sequence is where are the terms of this sequence going eventually? So once n gets really large, what value are we approaching? So remember the limit, when we learn in Calculus 1, the limit is what is the function doing as you're approaching a particular value. In this case, what are the terms of the sequence doing as we approach a very large n? So n is getting larger and larger. What number is that approaching? So, for instance, this one, n over n plus 1, we get 1/2, 2/3, 3/4, 4/5, 5/6. The 100th term would be 100 over 101. And you can see if you plot these on a number line, you can see what's happening. They're getting closer and closer together, and we're never going to get above 1. And then you can see it also on a graph. So this x-axis is the number of the sequence, what number of the sequence are you on? And then the y-axis is measuring the value of the sequence for that term. And you can see as you start off 1/2, 2/3, 3/4, 4/5, and so on, you get closer and closer to 1. So the limit, we're going to say the limit of the sequence as n approaches infinity equals L, just means that the terms of the sequence approach L as n becomes large. So n is always going to approach infinity, and the larger you get, I guess you never get close to infinity, but the larger n gets, the closer the terms of the sequence get to L. All right, so the intuitive definition. So we have the limit as n approaches infinity of a sub n equals L, or a sub n approaches L, goes to L as n goes to infinity. So if we can make the terms a sub n as close to L as we like by making n sufficiently large. So in other words, in this sequence, the limit is 1, so L would equal 1. So in other words, however close you want to get to 1, you can find a term in the sequence that will be that close to 1, and then all the terms after that will be that closer to 1. So if the limit exists, we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. So if we're plotting the points of a convergent sequence, it could look like this. These are just two versions. So in this case, we start below L. After 4 terms, we go above L, but then we just keep getting closer and closer, and apparently it never goes below L again, but we just keep getting closer and closer. Now, this one goes above L, below L, above, below, above, and so it just keeps fluctuating around L, but you can see it's getting closer and closer. The fluctuations are getting less and less. So those are two ways it can converge. Now, what happens if it diverges? Then there are a couple of different ways you can diverge. So one very famous sequence is just -1 to the n. And so what does this sequence look like? So if we start at 1, go to infinity, it would just be -1, 1, -1, 1, and so on. So then if we plot that, we have -1, 1, -1, 1, -1, 1. And so we're never getting close to any particular number. So that this would be a divergent sequence. So we say this one diverges. The other way is if you have one that goes to infinity. So the sequence, let's say 2 to the n. So this would be 2, 4, 8, 16, so on. You can see these are going to go up to infinity, so that would diverge as well. So either they don't settle down to a particular number, it's always bouncing around endlessly, or either increases to infinity or decreases to negative infinity. Either one of those, any of those would be divergent. Okay, so properties of these convergent sequences when we take the limits, and these are the same limit laws that you see in Calculus 1 when we talk about limits. So the sum of the limits, the limit of the sums, I guess you could say, is the sum of the limits. You can split the limit up between the sums or the differences. If you have a constant, you can pull the constant out in front. If you are multiplying, you can find the limit of each sequence individually and then multiply the limits together, or you can divide the two limits of the two sequences. Or if you have an exponent, you can find the limit of the sequence and then raise it to the exponent rather than raise each term to an exponent. Okay, so let's see how we can decide whether sequences converge or diverge. So we have this sequence 5n squared minus 1 over 2n squared plus 7. So we want to know, is this limit as n goes to infinity of 5n squared minus 1 over 2n squared plus 7? Does that come to a number, or does it go to infinity, negative infinity, or what? What happens? So if you remember from Calculus 1 how to do this, we're going to take whatever the biggest exponent with an n is. So in this case, we have n squared. We're going to divide every term by n squared. Sorry, that should be just 5. So 5n squared over n squared. So that'll just be a 5. So, whoops. Limit as n goes to infinity. Divide each term by n squared. So we get 5 minus 1 over n squared over 2 plus 7 over n squared. Now, bigger and bigger numbers, the 1 over n squared goes to 0. That goes to 0. That goes to 0. And so this is 5 halves. So since we have a finite answer, this sequence converges. All right, what about e to the 1 over n? So the limit as n goes to infinity e to the 1 over n. And so if we consider, we can put, so we don't have that law up here, but we can move this limit up into the exponent. So e to the limit as n approaches infinity of 1 over n. So now we're just going to consider this limit around the exponent. So this is perfectly fine. If you just have a number, you can move the limit into the exponent. So now what's the limit as n goes to infinity of 1 over n? Well, of course, n is getting bigger, 1 is staying the same, so this is going to go to 0. So this would be e to the 0, which is 1. So this one also converges. This one, we actually already did this one. We know this one diverges, so we'll skip that one. All right, what about ln of n plus 4 minus ln of n plus 1? So we need to find the limit as n goes to infinity of ln of n plus 4 minus ln of n plus 1. And so if you think plugging in bigger numbers for n, we're going to end up with infinity minus infinity, which doesn't help. So we know that is not going to work. So what can we do instead? Let's use the properties of logarithms and write this as ln of n plus 4 over n plus 1. And then kind of like we can do with the exponent here and move the limit into there, we can also do that with the ln function. So let's do this. And if you prefer, you can just kind of consider n plus 4 over n plus 1. Where does that go as n goes to infinity? So either way is fine. So what happens when we do this? So let's do this over here. So we're going to do the same thing we did with this one. We're going to divide everything by the biggest n exponent, which is just n to the first. We're going to divide everything by n. So we get 1 plus 4 over n over 1 plus 1 over n. 4 over n will go to 0, 1 over n will go to 0, and so this is just 1. So then we end up with ln of 1, which is 0. Okay. All right, then the last topic is what's known as the squeeze theorem. So the squeeze theorem is very interesting, and it comes up from time to time, probably pretty regularly. And so what this one says is you have 3 sequences here. So these are all sequences. We got A sub n, B sub n, C sub n. So these are all sequences. Now, for every term of A, well, after we get past a certain point, so n naught is just some number. So after a certain point, and we could kind of mark n naught here, but after a certain point, every term of A is less than or equal to every term of B, which is less than or equal to every term of C. So when that is true, and I got a little, this is a little typo, is n approaches infinity, A sub n equals that. So if we have Bn is always between A sub n and C sub n for all the terms that are greater than whatever this number is, and the limit of A is equal to the limit of C, then that tells us that the limit of B will also be equal to those. We're calling it L, but B is also going to equal these. So what that looks like in the graph is we have Cn is the biggest one. It's doing whatever it's doing. An is also doing whatever it's doing. Now, these are both going to go to, so if we imagine a line here, that's going to be where L is. So both of these are approaching L as n gets larger and larger. And then the trick is that B is always between these two. So B can do whatever it wants, but as An and Cn are getting closer to L, Bn also has to be getting closer to L. So that's the idea. There's no way that Bn can start coming up here, or even up here, even if it's not that far. It still has to be between A and C, and A and C are coming closer and closer to L, so they're squeezing B down. So that's why it's called the squeeze theorem. So that's the idea. Now, what does that look like? Well, determine whether the sequences converge or diverge. And so a lot of times, especially in this Calculus 2 class, we're going to be using the squeeze theorem with sine and cosine. So the reason we know that sine and cosine is always between -1 and 1. So whatever n is, this sequence is always between these two. Now, what if we divide both sides by n? We divide both sides by n. Now, why are we dividing by n? Because this is divided by n. So now here is our sequence. Now let's take the limit as n goes to infinity of all of these. So this should still be true. So take the limit of all three of these sequences. Now this will go to 0. This will go to 0. And so by the squeeze theorem, this one will also go to 0. So this tells us that the limit as n approaches infinity of sine of n over n equals 0. So this one converges. All right, similar thing here. So we have a sine squared, but still, we know that sine squared will be between -1 and 1, but even better than that, sine squared is always positive. So we could really say sine squared is always between 0 and 1. And then we can do the same thing. We're going to divide by this denominator. And then I won't write this step, but we're going to take the limit. If we take the limit, of course, this one is 0 for every term. That goes to 0 because it is 0 for every term. This one, 1 over 3n, will also go to 0 as n gets large. And so that tells us that this one will go to 0. So this one also converges. So that's how we use the squeeze theorem. So the squeeze theorem, very useful with trig sequences. And there are other sequences probably too, but trig is the main one that we're going to see. So get familiar with these. Next section, we're going to start with the infinite series. And this is where we're going to start adding the terms together and then see what happens after we add them all together. So that's where we're going. If you have any questions about this one, please let me know.